Alright, I'm going to make you a video here going through the book's explanation of replication, and I'll use their pictures. It'll be something you can go and reference and read. Uh, this is really almost impossible without someone verbally explaining this to you to kind of get the idea and understand what's going on. I mean, some people can do it, but reading this can be quite confusing without someone kind of going through it with you. I prefer videos like YouTube videos, but I've actually never made a video for replication before, so I figured, okay, let's go ahead and make one here. I don't teach replication in every course. Usually I do transcription and translation, but this course requires replication as well, so I might as well go ahead and do one for replication for the future. And the way to, we're going to start out here at 11.5 in the books. It says page 235 here. So if you have access either to the electronic book or the actual physical book, you're looking for section 11.5. And the book goes through some of the differences between bacteria and eukaryotes, or prokaryotes and eukaryotes. They don't do replication exactly the same. We're going to stick, I'm not going to make you learn the differences between the prokaryotes and the eukaryotes. You just need to know how we do it in eukaryotes. And of course, we start out with understanding that the fork, alright, they're going to talk about the fork, and that's just where you unzip the DNA at, where the point where it's going to come from. There are some proteins you need to make sure you know: helicase, topoisomerase, single-stranded binding proteins, and how they come together to make the fork. So there are a couple of pictures here. This one right here, figure 1115, is one you need to know. Now we can skip a few, and I'm going to tell you you can skip this one, and the next one we need to know is down here. Actually, you don't, we're going to talk about this one, but the actual steps and everything you need to know are down here at 11.20. Alright, so 11.20, alright, and let's see, 11.15 are the two you have to combine excuse me for answering the test. So the first one is, this one is just how do we form the fork. Alright, so our first part when you're explaining this is, well, how do we get this fork? Well, there are several proteins that are going to come together and they're going to create the fork. And in the case of these single-stranded binding proteins, these little beige or yellow proteins, they hold the fork open while the other proteins do stuff. But the initial opening of the fork is done by this one, helicase. But before you can do that, you have to use topoisomerase, this one right here. So I guess the first step is topoisomerase right here. So if you're going to write down steps, I would go 1. And you're going to say topoisomerase is going to straighten the DNA. Realize that the DNA is a double helix. That's like a ladder with a twist in it, or maybe a spiral staircase, however you want to think of it. And what we're going to do is we're going to straighten that ladder so that it's a straight ladder, and the thing that's going to do that is topoisomerase. So step one. So you're explaining this on the test. Step 1 is there's a protein out there called topoisomerase, and it straightens the DNA. That's our step 1. Step 2 is going to be, well, there's another protein out there called helicase. And helicase is going to kind of be the one that unzips the DNA. And, all right, now, the question is, which way is it unzipped? This says along the strand in the 5' to 3' separates the DNA. Well, it attaches to that one, and it on the 5' to 3'. So this was the one that kind of moves in the, I guess, in the opposite direction of the rest. But this one, you don't actually need to know which way it unzips it. You really just need to know unzips it. I think this is very confusing to students to explain it this way. But, and so I'm not even going to ask you which direction it unzips it, because you have 5' to 3' on that one, and 3' to 5' on that one. Which one is it unzipping from? Well, technically, yes, it's on this strand and it's going to move that way, but that confuses you on the second part. So just say that you don't have to tell me this. You just have to tell me that it is going to unzip the DNA in one direction or the other. All right? All you have to do is say this one binds first and straightens it, then the helicase binds and starts unzipping it. That's the important part, to know what these do. And then the single-stranded binding proteins come along here and keep it open. Now, if you just know that, so essentially you can think of this as 3 steps. If you want to do these steps 1, 2, 3, you could draw one picture like this. I think this is great. One picture about the opening of the fork, and then maybe you could give me 3 steps that go along with it. And the 3 steps involve what these proteins do. So you could go draw me a little picture on the test about like this. Tell me that topoisomerase is going to have to straighten it first, and then 2 helicase is going to attach and start the unzipping. That's what helicase does. And then you can tell me that single-stranded binding proteins are going to bind and keep the fork open so that these 2 don't come back together, so the other proteins can work on it. These are not going to interrupt what's going on. They're going to be there, but they're not necessarily going to draw them on the future pictures, but they're going to be there holding it open so the others can work. All right, so now let's jump down to, and we can skip this. All right, we can jump down to 11. They're doing bacteria there, and not exactly the same thing. Yes, 11.20 here. And here you can add 4 more steps. I like these 4 steps. There are other ways to explain this, but if you're going from the book, this is the best way to do it. And the next step, of course, is going to be there's this protein called primase. And primase is going to attach to each strand. In other words, there are multiple copies of primase, and of course it's going to find the DNA, and it's going to attach, and it's going to make what we call RNA primers. Now this is called DNA primase, so it sticks to DNA, all right, but it's going to make a copy, but it's going to make an RNA copy, kind of like RNA polymerase did. But it's not as good as RNA polymerase. It only makes a few, like 8 bases or something of RNA, and then it falls off. And so essentially this is going to be a complement, right? It's going to be a copy, complementary copy of the 3' on this direction, but it's going to be 3'. It always works in the 3 to 5'. So 3 to 5'. That's why that's confusing compared to the previous picture of which way it unzips. These are going to attach to each strand. All right, that's one thing. And both of them are going to make this in the 3 to 5 direction. In other words, it's going to read it 3 to 5. It's going to make it 5 to 3. It's going to read it 3 to 5 on this side and make it 5 to 3. So read the original, make the new stuff. So this is making RNA. So remember that this yellow piece here is RNA, and it's called a primer. And that's going to be the next step, is that, okay, we've got it unzipped. They've taken all those other proteins off, but those other proteins are continually moving down here. You don't see them here, but they're continually zipping this. And there are the single-stranded binding proteins. They're still along here. They just don't put them here because it's too cluttered if you do that. So that's why this picture is pretty good. The book does a good job. At least this book takes those things off and You got to remember that they're still there, but it does take them off to make this less confusing on one page. All right, so now that we have this primer made, all right, and remember that you're going to make them it's going to read the original 3 to 5. So this one is going to be it's going to be reading it and making things 3 to 5. The new DNA is being made 3 to 5. And up here, I'm sure I said that wrong. The new DNA, the original DNA is being read 3 to 5. All right, being read 3 to 5. It's making it 5 to 3. And that's the other hard part, is keeping track. Which one? 3 to 5, 5 to 3? I've tried to simplify that a little, even though I say it wrong sometimes. It's just too easy to say it wrong. But remember, this is heading, it's following the original 3 to 5. Following the original 3 to 5. Because the two strands are oriented in opposite directions, in other words, here we're 3 and here we're 5 and here we're 3 and 5, that's what causes us to have a leading strand and a lagging strand. And you do need to say that on the test to get full credit. And you need to say that the primer here on the leading strand is following the fork. All right? So it's going what? The fork is being kind of opened over here, and you're following the fork if you're following the 3 to 5 original strand. And that means you're making new DNA 5 to 3. Now, if you come back over here, though, you're opening the fork this way, but this primase is going to be operating in this direction. It's going to be going the opposite direction that the fork is opening. And this is going to be what we call the lagging strand. All right? And remember, this is DNA. And in DNA, this is RNA. The red is DNA, the yellow is RNA, and the only difference is that where you would normally have a T in DNA, you're going to have a U in RNA. So that's going to be a problem, but we're going to fix that in a second. All right, so we come down to this next piece, and what's going on over here is that after you have a primer, we made these little RNAs right here, and then these fall off after about 8 bases or so. And we made this yellow primer. Right here is the yellow primer. Right here's the yellow primer. Right here is the yellow primer. So they're RNA pieces stuck to the red DNA here. Well, notice this one is following. This is the leading strand. And this is what's going to allow, the primer is what allows DNA polymerase 3. Now, you do have to know the difference between 1 and 3 here. So when we do RNA polymerase, we only learn about one of them. There are many RNA polymerases as well, but we only needed to know one. Here, DNA polymerase 3 has a unique function. It's going to attach to a primer, and then it is going to move along the strand 3 to 5. So the original strand, it's going to attach to that and move in that direction and follow the fork. That is the leading strand, because the DNA polymerase 3 is following the fork. Now, unfortunately, this one down here is going to attach to a primer, and it's going to be going in the opposite direction of the fork. And so it's going to run out of room here, and it's going to fall off. So it's only going to make the new DNA for a little while and then fall off. And that is, when it does that, it calls it an Okazaki fragment. So it has a little primer and some DNA, but it can't keep going, so it falls off. And when it falls off, it's going to loop back up here, and notice that as this unzips on this side, you can now make a new primer. So while this was being made, this one right here made another little primer back here. All right, and so that means when this falls off, it can go and attach right here to this primer, and eventually this piece is going to make some DNA right here that we're going to see in a second. Now, after you have made the couple of pieces, so there are a couple of pieces that have been made, you're going to come along and you're going to have to fix this. These Okazaki fragments right here, they need, the RNA needs to be turned back into DNA. You need to turn the U's into T's. all right? And then you're going to have to connect all of them. So we have a couple of proteins here that are going to come back and do that for you. And that's the first one here is DNA polymerase 1. And what it's going to do, it has the ability, we'll read this, you can read this little thing here. DNA polymerase 3 elongates the strand. All right, that's the one that's following the fork or making the Okazaki fragments. But DNA polymerase 1 removes the primer and replaces it with DNA. And what that means is it doesn't actually remove all the bases. It just turns uracils into thymines. It takes the U's and turns them into T's. So it sounds like it's replacing all of this, and it's no, not really. I mean, it's altering it chemically, yes, but it's essentially turning the uracils to thymines, and that, of course, would make that DNA. There is another chemical reaction that has to occur, but we don't need to know it. But we can say that basically it turns that little piece of RNA, the little yellow piece, into DNA. And so DNA polymerase 1 solves the problem of removing the primer and basically making the whole strand there DNA. But that's not the only thing that needs to be done. Once you have these little Okazaki fragments and then you change the RNA to DNA, you then have to connect them. They are still fragments. And the fragments, all right, need to be connected. And the protein that comes along and does that is DNA ligase. And it creates a covalent bond between each of the fragments. So right here, the fragments were not connected. You had you had DNA here, you had DNA here, but there was a covalent bond missing between the two fragments, and ligase comes along and adds that bond. All right. Here you see another primer and another primer here. Those will eventually be changed into DNA by DNA polymerase 1. But right now they are still primers and they are not linked. There's still a gap between any of these. Notice up here on the leading strand, it's just going along on its merry way, and it doesn't have to worry about any of this stuff. So ligase is kind of your last step. All right, ligase is the one that actually connects the DNA that has been converted from RNA to DNA to the next Okazaki fragment. So because these fragments are not connected, you have to add one bond across there, and that's what ligase does. And that's basically what you need to know. You need to know these 4 steps, more or less. If you want to draw this the way they do, that's fine. I suggest actually making your own version, but you can take these 4 steps along with the picture up here, and kind of explaining how the fork opens. So maybe I think a good way, if you're copying the book, would be to start with this picture and make your own version of that picture. All right, and explain what's going on. You can explain it by explaining what the proteins do. This one takes several pictures, several steps to explain down here, and I think the book does a reasonably good. I've seen better, but you can go by these pictures in the book and do something very similar. The best way to do this is probably by each picture you add another protein and show what it's doing. But you do need to show that the leading strand, and explain in your verbal explanation that the leading strand is different from the lagging strand. All right, and explain that 3' to 5'. But I would look at those 2 pictures. I think what was it, 11:15 up there and 11:20 down here. Those are your 2 best pictures to go from. You can read it. Here are a list of the proteins, more or less. You have DNA helicase. You have single-stranded binding proteins. You have topoisomerase. You have primase. You have DNA polymerase, you have DNA ligase. Um, know that you have two DNA polymerases. Um, there are two of those. There's 1 and 3. So this is kind of misleading. They leave out the distinction between DNA polymerase 1 and DNA polymerase 3. So, but these are essentially your proteins. All right, here they're showing you that there is a gap. There's an Okazaki fragment. These two pieces are not bonded. There's a gap right here. See how the DNA is continuous, but here are your two Okazaki fragments, and this little piece of RNA is not connected to this piece of DNA. The DNA is blue, the RNA is yellow, and these fragments, not only do you need to convert the yellow to blue, in other words RNA to DNA, but you also then need to connect them. And remember, we have two proteins to do that. So here they're showing this, they've kind of fixed the DNA here, but there's still a gap. All right, they've gotten rid of the RNA, it's now all DNA, but you're still going to have to fill that in, and ligase is going to do that. DNA polymerase 1 is going to be the one that converts the RNA to DNA. So DNA polymerase 1 is going to fix that. All right, that's how you end up with the extra DNA here, and then you basically link them together. Beyond that, there are some differences between the names of these proteins between eukaryotes and prokaryotes. We're going to stick to eukaryotes. You don't have to know. It's almost the same, just change the names in bacteria or prokaryotes. Telomerase, you should know a little bit about. I talked about it in class. You should go through and maybe read this. This happens at the end of the chromosomes and has to do with aging. And I talked a little bit about it if you want to read about it. But that should do it. I think if you follow along here and you kind of look at these pictures and can describe what's going on, I think a good way to organize this would be to take the 11.15 picture and draw it, or your version of it, and write your explanation underneath it, and then you could do these 4 pictures and write an explanation under those. Do I think you should memorize it? No, I absolutely. You need to discuss it as in your words. Just describe it as you know it. I suggest telling the story to someone else if you can study with someone else from the class. I would suggest going through and just verbally taking these pictures and describing what's going on to someone else. And let them correct you and go like, hey, no, I don't think it works that way, or maybe a better way to describe it is this, or you left out this step. And go back and forth until you get all of this, and you can just talk about it. If you can just talk about it and kind of tell the steps, maybe you have the pictures in front of you and you just get where you can just talk about what's going on. Maybe you need a list of the proteins and some pictures. You figure out what the proteins do, and then you kind of learn to draw what the pictures do next. Learn to draw the pictures, and then just kind of slowly put it together. I think you can do this. This takes a while to learn and to get it down. I know that this is not a simple thing to learn. It takes a while to go through and put it all together. But I think, yes, 11:15 and 11:20 are your best bets for explaining this on the test. And that's it.